Good. Hi, good afternoon, everybody. Thank you for the conference, giving me such an opportunity to present my recent research on the Gaussian process. Here, my title is the two-layer mixture of Gaussian process for cover, clustering, and prediction. I'm from the Peking University School of Mathematics, so my background is mathematics, so I focus on the mathematical model and algorithm here. So maybe somebody not very familiar with this field. So here I will introduce the Gaussian process GP model and the mixture of Gaussian process MGP model here. So another special GP model is a Gaussian process fractional recursion, GPFR, we will use in our model. So here is the introduction. Our model is, real model is the two-layer mixture of GPFRs. So we call the TM GPFR. The learning algorithm here for this model is the MCMC EM algorithm. We propose this algorithm for this model. We give some typical experiment results and comparisons, and finally the conclusion and future works. Firstly, we go to the GP model. GP model came from the Gaussian process. Gaussian process is a very typical stochastic process in which any finite component, number of components or states and different time are subject to a Gaussian or normal distribution. It is widely used. It is become a powerful tool of machine learning and widely used in the modeling and analysis of time series, such as regression, prediction, and classification. That it can describe the mathematical relation between input and output like a neural network, but different also reflects the change with time, which introduces the view of time on the information process. So this is quite different. So it has the time relation between the inputs and outputs, the pairs. Mathematical model is here. It is definition of GP like this. For pair of given time series x and y here, x is S1 to x capital N is as the input. Y is output, y1 to yn. Mean ya corresponds to xa. If y is subject to a normal distribution like this, ms here is a mean function, and here is a convergence matrix with kxa. Here each element is a kernel function with xi minus sg square, and here and plus sigma square a is a normal noise. If y is subject to a normal distribution like this, y is called a Gaussian process with input x. This is a GP model. From the model, we can say that a GP process here is a standard process. Recently, about almost 20 years now, Gaussian process can be applied for regression and prediction. That is, its parameter can be learned from given data, and the future output can be predicted by the expectation for a given input value and a given input volume. Moreover, it can be used for binary classification, setting the output to be a binary. So for classification of x input. But just as I said, Gaussian process in this way is just a stationary process, not the in-station. Now, for solving the modeling of the multimodal depth on stationary many model, the mixture of Gaussian process has been proposed or used in which a number of GPs are linearly mixed together. In general, these GPs are mixed along the input of the time region. Actually, they can also mix along the output region. This is another kind of MGP. In MGP model G, the number of the GPs, here we call Z A and G, will increase with the complexity of data structure, and therefore the number of parameters increases exponentially. Although the ability of one GP is limited to on learning a stationary time series, MGP can be powerful enough for any learning task on as long as G is large enough. So attention here. The number parameter is an important index of complexity of a model now. In general, the number of parameter become large, the model gets more complicated and more powerful, which can therefore decrease its generalization ability and lead to the overfitting problem. So this is a contradiction on the number G. When G is lower or small, the learning ability is limited. But when it's large, learning ability is increased, but generalization ability become poor. So this is a GP model. As for MGP model, so we now from the GP model to the MGP model. As for the MGP model, it's clear. Here, this is a architecture of a feed-forward neural network like this from here to here. But for the mixture of the Gaussian process MGP, here is a get function and fuse this GP together. This is the MGP model. We now see the mathematical model like this. Suppose that there is a given set of n sample D like this, as n and when, n from 1 to capital N. So is a capital N pair of samples given, where as n and when are the volume of input and output and time n respectively. This is given that. We need to learn the model, MGP model from this data set. The association of sample S and when with respect to the components when 1 to J Gaussian process is described by a indicator variable ZGN, which is subject to a probability distribute like this, very simple. That means there are capital G components or GP process, GPs. So here, n small n sample indicate to G is like this. When ZNG is 1, means this sample belongs to this GP company or GIS company. This is very simple, only for 2 components or 2 GPs process. The input variable of one company is subject to a Gaussian distribution like this, meaning when the sample is belong to the GIS company, Sn belong to this Gaussian distribution. very simple. The output variable of one company is subject to Gaussian process with zero mean fraction. This is very simple. Means VG is subject to GP x theta j. Means now we here. Sorry. Here. Here. Just means that this is GP, the mean is 0. Theta g is just the parameters of the converse matrix on the assumption that this kind of MGP is fused along the input or time region being mixed linearly. So only mixed along the input or time region. We now go to the parameter learning. For the parameter learning, the EM algorithm is a general parameter learning method for the model with a hidden variable or incomplete data. Since the indicator variable of the samples with respect to the company can be considered as a hidden variable, the EM algorithm is widely used for the learning parameter of the mixture model. So the EM algorithm is often used for learning the parameter of the mixture model. And for the parameter learning of MGP, it is quite different. The EM algorithm is often used, but it became difficult to be realized because the sample points are not independent, such as Q fraction involved in the expectation step cannot be computed directly. So in this way, we must use some approximation strategies to simplify the computation of Q fraction. Along this direction, there have been some approximate or modified EM algorithm, such as variational Bayes, leave one out cross validation, LOOCV, hard-cut, sparse sampling, and MCMC-based EM algorithm. This is just our work done on this algorithm. There are also some variational Bayes inference of the MCMC sampling method directly for the parameter learning estimation of MGP model, which generally cannot lead to a good result due to the unreasonable assumption. And for the variation Bayes, we need suppose that the parameters should be independent, but in many cases they are not. Or rough approximation, that means sampling are very time-consuming. There are another important problem for the MGP. This is the model selection. For the finite mixture modeling, it is very important and challenging to select a number of components, which is generally referred to as a model selection. Why? Because a number of components really is a model. So as it changes, there are many models. So select a number of components, it just makes a model selection. Since the states of stochastic process are related along the time region, they are not independent. So the model select problem of MGP became more difficult as it cannot be solved by the conventional methods such like ASC or BSC. These are the model selection criteria. Recently, we have found the balanced relation between the number of samples and the number of components and proposed some closenessly balancing criterion called SBC for the MGPs with missing along the time region. This is a new break on the model selection of the MGP. According to the MBC, we further propose a dynamic split and merging EM algorithm for the MGPs, which can make model selection adaptively and dynamically during pyramid learning. By utilizing the resolvable jump Markov chain Monte Carlo model and method for the MGP model, we can design the moves and transition for the final equalization and stability. After its convergence, we can get the probability distribution on the possible number of components as a complete prediction of model selection. This also gives a probability on each possible number of components. We now see an example of MGP. Here we see this. There are a typical data set of MGP model with 3 Gaussian processes in the different colors. With this MGP model, we can model a non-stationary or multi-model, 3 model now together, multi-model stochastic process with different Gaussian process in the separate input region. Here is mean fraction, or the mean fraction of each component is supposed to be 0. So we need 3 components on different time together to model a process, a stochastic process like this, a time series. But in some cases, this cannot work. So we go to another model, Gaussian process fractional recursion. Here, the action data of a paralyzed patient are typical fraction that occurs. For each action, there are many curves and different time, not just one curve. So before that, the MG model or Gaussian learn one curve or a time series. But now, there may be many different curves. It is very challenging to make curve clustering analysis for action recognition, which cannot be solved via the MG model, missing along the time region. We need to consider the GPFR model for the MGP model missing in the output space, not the input space. This is GPFR. Really, it is very simple, like this. Here, curves are classed into 2 classes here. One is in the black, one is in red. These clustering results are obtained by the learning of the mixture of GPFRs. The mixture, they call the mixture GPF model, in which GPFR model with a non-zero mean fraction, not the 0 mean fraction, non-zero fraction, that can be expressed as a linear combination of basis fraction whose missing proportion can be learned in a regression mode. This is a model of the GPFR. Given a data set D like this, here SMN, YMN, M from 1 to capital M, N from 1 to capital N, M, where M is the number of curves, NM is the number of sample points in the M's curve. Suppose that there are k type of curves. Indicate variable of the M's curve with respect to the type of class K is ZKM, which is also subject to a probability distribution. The GPFR model, whereas here we call the GPFRS BK theta K. Theta K is the same as previous GP model. It is a parameter of the covariance matrix, but BK is different now. BK is a parameter for the mean fraction. Mean fraction MK is sum A from 1 to B. BKA CICS. Here, H1s, HBs is a group of given basic function, like a system of sparse functions. So here. But anyway, the GPFR model is still a Gaussian process, so that the mixture of GPFR can only describe general stochastic process. Okay, just one process, a general stochastic process. Oh, no. Now we go to our model. We call the two-layer mixture of GPFR, the GTM GPFR model. Why? For a set of curve from multiple sources or general stochastic process, means the curve from different sources have different stochastic process and generate from a mixture of some general stochastic process, not the Gaussian process. Here, we cannot model this data by a mixture of Gaussian process, including the mixture of GPFR, because GPFR is also a Gaussian process, not the general process. So, as the MGP can model a stochastic process, we can mix some MGPs together to some sources mixing together, which lead to the idea of two-layer mixture of Gaussian process. In fact, we proved a two-layer mixture model of Gaussian process functional recreation to describe such a mixture of general stochastic process or independent sources, especially for curve, clustering, and prediction. This is the detail given in these papers. The paper is published in the IEEE Translation on Neural Network and the Learning System. We now give the idea of this model. Like this. This is ST, is the input, weight is here. Now, there are some basis GP models here, G1, GP1, GPJ, GPM. So there are. From these GP models mixing together in this is the lower layer, this high layer. High layer, there are some MGPs, MGP1, MGPI, MGPN. So there are N M mixture of Gaussian process. Then together we have weighting. We linearly mixing them together by pi 1, pi A, pi N together. We have the weighting. This is our idea. Certainly, weighting can be considered as a together as a mixture of Gaussian process, but here we have the two-layer structure. When we know this two-layer structure, we know the sources here, 1, 2, N. So this is our model. We call it two-layer mixture of GPFRs. For type curve from a stochastic process, which may be multimodal and non-stationary. So we need to utilize MGP model mixed along the time region to model them. For more accurate modeling, each GP can be replaced by the GPFR with a non-zero mean function. This is more accurate. Therefore, we can use a mixture of GPFR. We call shortly MGPFR to describe some one source. One source is described by a MGPFR. We further mix these GPFR together to construct a two-layer mixture of GPFRs. We call TM GPFR to model this linearly mixture source together. For the parameter learning of the TM GPFR model, we design the MCMC EM algorithm. It has been demonstrated by the experiment result that the MGPFR model, outperforms the other mixture models on both curve clustering and prediction. We now see the detailed model. Here, given the curve dataset D, DSMN, YMN, M from 1 to capital N, M, N from 1 to N, capital N, M, just like the MGPFR, where M is the number of curves, N is the number of sum points in the M's curve. The indicator variable of M's curve with respect to the top of all cluster of K, or source coin, is ZKM, which is subject to a probability distribution like this. So we mean there are capital K sources. The indicator variable of some points xm and ym with respect to the GPFR of class K is ZG under KMN, which is subject to a probability like this. The input variable SM under ZKGMN is 1, is subject to a normal distribution, and the output of GPM model is a Gaussian process. So this together is RO model, detailed model. Here, this is a parameter. In the rod is a parameter. Here is a variable. This variable we describe the which sample belong to which class, which GP component, and which cluster or classes. In this way. How to decide the MCMC EM algorithm? Construct the likelihood function of TM GPFR model. L set Z8. We need the likelihood function, where theta is a set of all the parameters. Z here, capital Z, is a tensor of hidden variable in the lower layer, mean which sample belong to which GP component. And A, while A is a matrix of hidden variable in the high layer, which curve belong to which sources. So now, for the two-layer mixture model, it's difficult to derive the Q function, since there are two kinds of hidden variables. We can take the double expectation to solve the Q function in this way. First is A, another is Z. However, the computation of Q function is exponential and cannot be computed directly. The MCMC estimator of Q function in this way, where we sample the ZA. For the Z, the S sampling of Z, which is a approximation of Q function in this way. So in this way, we can know, we can have the MCMC EM algorithm. The step of M like this: initial theta. We can use the MCMC method to generate the samples of the hidden variable in the lower layer, Z1 to Z capital II. Compute the indicator variable in the high layer. We can use this computer this alpha K M1, alpha K Mi, and get the Q function. Maximal the capital Q function and obtain the Q estimator. If the modification is small enough, stop, and otherwise turn to the step 2 and continue iteration. And finally, we get the parameter set. We now see the result. We can see there are two kinds of covers. It is a sketch of a typical sensitive data set for two cover clusters. Each cluster has 10 covers. One is red, one is in black. If there are no color, we cannot separate them, these two clusters, which are very difficult to be separated. We have three such synthetic data sets. This is the original one, and another one is a small samples, and another one is unbalanced one. There is the two sets have the same number of cover. We can to other data sets. We can see the result from our model. Here in the higher table is here. This is the model. This is our two-layer model. This is a mixture of the GPFR model. This is a mixture of GP. We mean the mean the mean function is 0. 3 models and 3 results. Original data, small data set, and unbalanced data set. Our model, this is a result of the cover classification. Our model can make the clustering analysis very well. We can divide two types of clusters clearly. Only one error in the small data set. But the other model cannot do that. They are much poorer than our result. We almost wrong. This is a prediction result on the lower tab. This is a result of root mean square error. This is an original small unbalanced data set result. Each case we get the best result, but the time is very consuming. But think the model is so complicated, so our time is large, but we can get the best prediction result. We now see some practical applications. These are two data sets. One is electrical load, another is weather. From here, this is real world data, so we didn't know the K. So we use some method to find K, G, and D cross variation. We can find our model can still predict very well in each case. We can also get the result on the cover classification. We give the cover clustering result here. Really, we get two types of covers. Here is very clear. This is electrical load from day, each day, so we can find the two kinds of days. The load, electrical load are different. Here is a weather. We can find two kinds of weather condition in different places. So this practical application quite well and very significant. We now go to the conclusion and field work. Firstly, the MGP model can model a general non-stationary stochastic process with a given data set. There is some feasible algorithm for both parameter learning and model selection. However, there are still many problems on this learning algorithm to be solved or improved in the future. We do such work for almost 10 years, so many algorithms in this way. This is a new model here. The TM-GPFR model is a development of the MGP model and can solve the multi-sources problem. Here is solve the multi-model problem. Here is solve the multi-sources problem. But it's more difficult and complicated to solve the parameter learning and model select problem. Oh, there are still many things should study. The learning of MGP model is still very slow now in comparison with the modern neural network. However, it is more accurate and effective on modeling the data set, especially time series. The sparse MGP model can speed up the learning, which can be applied to the learning of the TM-GPFR model. So that's all. Thank you very much.